All right. So today we're going to talk about gases and pressure. And that's going to basically set you up to do, you're actually going to develop the equation for that we're going to use today, or that we're going to look at today. You're actually going to do part of the original experiment that was originally used to develop these experiments. We're going to kind of consider some of the variables that go into describing gases. But for starters, we'll start with stoichiometry practice. I know this one's got a little bit different. It's not just a theoretical yield, or it's closer to a percent yield problem. Let's say we left a piece of iron outside all winter, and we came back in the spring. Some of it had turned into iron 3 oxide. What percentage of the iron has reacted to form iron 3 oxide? How do we figure that out? Start by balancing. Always a good first place, right? And how do we need to balance this?
Or we double the iron oxide or
We're gonna have to double the iron oxide. Why? Odd number. Then that means we can put a 3 there, and then all we have left is to do the iron at the end, right? Like you just said. All right. We have an initial amount of iron, 115.6 grams. And then we have a final mass of 142.8. How do we know how much of the iron has reacted? What could we do with that? We could put it in moles.
I know.
Oh, I know I'm getting old. I can't find the mouse cursor anymore unless I make it really big. I just deleted a number. What was that number? And how do we, where did that come from? Yeah, how do we know how many grams of oxygen we had that we added to our system? We know that everything that reacted formed Fe2O3. So if we look at the difference between these two numbers, that'll tell us how many grams of oxygen reacted. So putting that number back in there. 27.2 grams. Now we have some numbers we can put into moles. Landon? Yeah, that's the iron oxide plus the unreacted iron. Because think about what this is physically saying. It's a piece of metal that you left out, and you weighed it before you left it out all winter, and then you weighed it again after. The weight went up. That doesn't mean all of it reacted. So it's not like we can say all 142.8 grams is iron 3 oxide. What changed was we added some oxygen to the existing iron. Right, so we don't actually know how many grams of iron 3 oxide we have. That's what we're trying to figure out. How are we going to figure that out though? Well, we know how many moles of oxygen react or grams of oxygen reacted, right? So we can use that to say, okay, well, 27.2 grams of oxygen reacted. How many moles of product is that? And then we can figure out our percent yield, what percentage of our 115.6 grams reacted. Yeah. Well, think about this physical reaction. You've picked up a piece of rusty metal before, right? You can weigh that, right? That's the iron oxide mixed with the iron, right? So we can't weigh the oxygen directly when it's a gas because it's a gas, but we can do this same exact experiment. Say, well, the amount that the mass is different must be the mass of oxygen. So basically by doing a subtraction, that gives us the oxygen since we can't weigh the oxygen directly. Does that make sense? All right. So now we've got grams of things right here. Now what do we do? Somebody already said it once. Put them in moles. When in doubt, put everything in moles. So that's going to give us, what, a little over 2 moles of iron. 115.6 grams of iron. And there is it 55.4845. So 115 divided by 55 is going to be 2.0 something. How many sig figs are we going to want to keep though? 4, right? So 2.07. Perfect. And then how many moles of O2 is that? We do the same thing. It's going to be, say that. How many sig figs are we going to keep here? Oh, 850. Thank you. Did you double the mass of oxygen? So they're not being used up at the same rate, but they're being used up at close to the same rate, 4-to-3 ratio. We have more than 1.33 times as much iron. So we can have a pretty good guess of what's going to run out first, especially since the question said what percentage the iron has reacted. We're probably not at 100% yield. But just to show that, if all of our oxygen reacted, how many moles of iron reacted? Well, 0.0850 moles of O2 for every 3 moles of O2. It's 4 moles iron reacted or used. So over 3 times 4, it's going to be 1.1 something. And we're only going to keep 3 sig figs though, right? That's moles of iron used. Do we have more iron than that to start with? So what's running out first? The oxygen. And really, it's not like the oxygen's really running out in this case. It could just be we didn't give it a long enough time. If we let this chunk of iron react long enough, it would turn entirely into iron oxide. But given the situation that's described here, we know that only this many grams of oxygen reacted. That's not to say we actually ran out of oxygen though, right? Does that kind of make sense? We're kind of treating it like it's a theoret or like it's a limiting reactant because it's not done reacting yet. And we have less moles of the oxygen here. Is this enough to answer our question? We need a percentage. Percentage of what? Iron that reacted and iron that we started with, right? So we're only one step away. We're close. All right, if we want the percent that reacted, what's our formula? Part over the whole. What's the part? And what's whole? 1.13. And our total is that the second Austin Powers movie or the first Austin Powers movie where they keep making that joke the whole time on the whole? That's the third one. Yeah. I'll say total instead of whole. How about that? Part over total. So 1.13 moles of iron reacted. 2.070 is what we started with. Times 100. So we'll get something close to 2/3. 54. Could we have done some slightly different math steps to get to the same answer? Yeah, there's a lot of different ways we could have gotten that. We could have done done it as theoretical yield and gotten how many moles of this product were made, and then turned that into moles of iron in the product, and then we would have wound up with the same 1.13 moles of iron in the product that we had here. It would have just been a more roundabout way of doing it, but we could have gotten there a lot of different ways, right? All right. So it seems like stoichiometry is getting better, right? We're just going to keep hammering away at it till it's second nature. So every time you get a chemical reaction and with amounts, your first thought is, I'm going to have to do some stoichiometry. All right, questions on this one? All right. Oh. All right, so let's talk about another way we can do stoichiometry. One of the trickiest things for in stoichiometry sometimes is figuring out how to get to moles of stuff, right? It was a little bit tricky in that last one, figuring out how to get to moles of oxygen. And is it Aliana that asked about, well, how do we weigh how many grams of oxygen we had in there? Gases make things tricky, right? Solutions made things a little tricky. We had to use concentrations and stoichiometry. pH makes things a little tricky, but they're all just different ways of talking about how many moles you have, right? So when we're dealing with gases, we have some other variables to take into consideration. When we were talking about concentration, what variables wound up being really important if we were trying to figure out concentration or go from concentration to a number of moles? What did we have to do? We needed molarity. So would it have been enough to say that our oxygen was 0.100 molar? What else do we need? We need a volume, right? So there are really two variables if we're trying to figure out from a constant or a solution. Gases, it turns out there's some variables too. Can anybody think of what variables affect gases? Pressure. What is pressure? How condensed it is. So that kind of sounds like it's a concentration, right, Miri? It's kind of like density, just the same way that so density was mass over volume, right? And concentration was moles over volume. So density of a gas would be kind of like a concentration. That would be one way we could do it. If we knew the density of a gas, we could use that like a concentration to get grams, right? We had density and a volume. So very similar to what we did here. Anybody think of any other variables that affect gases or pressures or densities? Temperature. What did you say, Lisa? Oh, sorry, Lila. Temperature is going to affect things too. Do we have to worry about temperature when we're talking about solutions? No, not really, right? If we had a concentration, that's all we really needed. The trick with gases is that their density is partially dependent on temperature. So it's not just enough to say that I've got oxygen gas and then look up a density, right? The density of a gas is variable based on things like temperature and pressure. All right, so back in let's see, this probably would have been in the 1700s. They started looking at, and this is really more of a physics question at first. They started looking at how do we describe gases and what kind of variables might be linked together. And so they started looking at realizing that if you had, let's say we blew up a balloon, there's gas inside that balloon, right? What's holding that balloon open, I guess, or stretched out?
Gas.
The gas. But what's the gas doing to cause that? It's exerting pressure. It's pushing on something, right? So basically, if we think of the gas molecules as molecules, basically they're just constantly flying around in random patterns and running into things. Well, if you trap enough gas molecules inside of a container, then yeah, every single gas molecule that bumps into the edge of the container or into the container itself is going to push on the container a little bit, right? Like throwing ping pong balls at your bedroom door. If your bedroom door is partly open, you could eventually throw enough ping pong balls from your bed so that you could close your door without getting up, right? It might take a lot of ping pong balls, but every single ping pong ball is going to exert a little bit of force on the door, right? Yeah, can everybody visualize that? Now think about the gas molecules as ping pong balls. If you have enough of them, they start adding up to a measurable force. And that's what pressure, gas pressure really is. It's just basically the sum of all of the gas molecules running into something. Jesse?
Less density for reasonable force, like through a tennis ball.
Kind of, except you have to put more energy into it if you're throwing a tennis ball versus a ping pong ball, right? The tennis ball let's ignore air resistance. If you throw a ping pong ball really, really hard and there's no air resistance, it's going to hit the door with a lot of force, just the same amount of force that a tennis ball would, right? If you put the same amount of energy into it with your throw. So it turns out that the force these molecules exert, force in physics is defined as, who's taking physics in here? Anybody? In it right now, who knows this equation I'm about to write? F equals ma. What's m? Mass, and what's a? Acceleration. So basically, for the same amount of force, it's going to be dependent on both the acceleration and the mass of the object. And that applies to the force that you put into it as well. And then it turns out that if you apply a force, the force times a time, is that the right? Yeah. Force times a distance gives you been a long time since I took my kinematics. What is the equation for kinetic energy? 1/2 but mv squared. Which is not quite the same as acceleration. I don't remember the derivation for this one off the top of my head. I'm sure we could work it out, but I'm not, that's beyond what we're trying to do right here. Basically, different molecules are going to have the same average kinetic energy at a certain temperature, which means that the mass is not really going to affect that. And so it doesn't really matter how big the object is. It's just about what their average kinetic energy is. You take the throwing a ball at your door to the extreme. If you threw a bowling ball at your door to close it, it would close it, right? But that's more work. You'd have to put more energy in than just getting up and closing your door at that point, right? Because you had to accelerate that bowling ball the whole distance as well. And then you break your door and everybody gets upset at you. And then there's no point in closing it anyway. What about if you threw an entire box of ping pong balls at once? Could you throw that hard enough to get your door to close?
Yeah.
Probably, if you added up all of that force at once. It might be a ton of tiny impacts, but if you apply enough of them, you get a measurable force.
Like the same, it's like throwing.
If you ignore friction, it would be the same amount. It doesn't matter if they hit all at once or if they hit one at a time, if we're ignoring air resistance and friction, which everybody in physics knows we do that all the time, because it turns out air resistance and friction you start to include pretty early on, but air resistance, you have to take differential equations to be able to do the math. Because what happens to air resistance as you speed something up? It gets stronger, right? So basically your air resistance is not a constant force slowing something down, it's a variable force, and the force of the air resistance depends on how fast the object is moving. And that's what we call a differential equation, because the faster the object moves, the more air resistance you get. So basically, a lot of times we wind up ignoring air resistance. And really what air resistance is from the scale we're talking about right now is basically all those tiny gas molecules getting pushed out of the way. If you throw something, all those tiny gas molecules are pushing back against that object that's moving. Mary?
I don't know, like you kind of just described it, so like it reacts to the different changes like around it rather than.
Yes. And it might make the point that you're trying to ask. The gas molecules aren't in the air, the gas molecules are the air, right? So gas molecules are just tiny molecules floating around in a vacuum, but you put enough of them together and they start getting in the way of other objects moving. There's a question over here. Yeah.
What's the difference between a differential and an exponential?
A differential usually means that the term you're trying to describe is in the equation for itself. So your air resistance is based on is the force. That's not the best one to include, but so for chemical reactions, you can think of the rate of a chemical reaction is the change in concentration of one of your reactants over the change in time. And that's that rate, that equation is equal to K times a constant times the variable itself. So that is going to make things really hard to do any sort of calculus with it when the term you're trying to take the differential for is in the function itself. And that's why DiffEq is its own class. Basically, just the air resistance is what slows things down. It's the reason that a golf ball and a ping pong ball, the golf ball will go faster because it's heavier, so it can push those air molecules out of the way better. All right, so if we have all these gas molecules running into the edge of the container, we could sum up all of their interactions and say that inside that balloon that we started talking about, inside that balloon, there's a certain amount of force, and that total force is going to be all of those individual collisions added together, right? But the thing is, we don't usually just look at total forces. A lot of times we look at a total force sort of normalized by some other variable. So let's say that instead of throwing ping pong balls or tennis balls at your bedroom door, you started throwing darts at it. That could conceivably also work, right? If you're throwing with the same amount of force, what's going to happen to the door, though? You're going to start putting holes in your door, right? How come the ping pong ball doesn't do that? Because, well, there's the fins on the back of the dart, but what if I put fins on the back of a ping pong ball? It's still not going to really do anything, right? What's different? It's sharp. What does sharp mean? Pointy? It goes to a point. We're putting the same amount of force in a smaller area, and it is more aerodynamic too. But we could make a dart, like think about a Nerf dart then. Nerf dart still is aerodynamic. You can still throw it just as hard as a dart, but a Nerf dart's not going to put a hole in your door. It's because of that area at the tip. Anything that's sharp, it just means it has a really, really small area. Like if I took the edge of this calculator and I tried to cut, I don't know, an apple with it, is that going to work? I mean, eventually, if I hit it hard enough, right? But I would have to go a lot harder. If I had a very sharp knife, I wouldn't have to put much force on it to get it to go through the apple the same way, right? The difference between those is that force is not the same as pressure. Pressure is force spread over an area. So the definition of pressure is a force over capital A this time for area. What happens if you have the same amount of force but a smaller area? What happens to your pressure? If your area goes down, your pressure goes up for the same amount of force. So that's the difference between using the edge of the calculator to cut an apple and using a knife. The only difference is the area. And it turns out that's what's going to be the difference between pressure and force. And this is why sharp knives cut things better with less force than dull knives. A dull knife just means it's rounded like like at the microscopic level, it's rounded like the edge of the calculator. In a sharp knife, you just take that and you just make it so it's a smaller area, and all of a sudden it'll cut better. Just say.
What's the difference?
Scale. There really isn't a whole lot of difference. If you hit something with enough force over a bigger area, you can still apply just as much pressure, which is why you can still wind up with things like, yeah, if somebody gets into a car accident, it doesn't matter that the car has a very big area because it's such a large force. It can still exert a ton of pressure on your skin. What was that? And that's where air resistance comes into it.
What was the question?
Sorry, the question was about how the weight of the object affects things. You have to put more energy into it to throw that metal object, though, right? And so that's it. It just keeps things that are more dense are less affected by air resistance because they're able to keep more of that energy you put into it. They hit fewer air molecules on their way through the air. Brody and then Macy.
Why is this a rated knife?
Because you added a ton of tiny points to it, right? Which means you decreased your area. Macy?
Using something denser would be like counterproductive, then it comes to more energy input.
It depends if we're taking air resistance into account. If we assume no air resistance, then it shouldn't make a difference. You have to put the same amount of energy in regardless of how heavy the object is. It just means that your ping pong ball would be going that much faster than the golf ball. Lila?
If you're decreasing the area, wouldn't that make the number right side of the equation larger? Like if the force is the same, so then wouldn't the pressure like, when you want like less pressure in areas, like you don't have to put as much pressure in areas.
You don't need, yeah, it would be overkill for me to take a sharp knife and hit that apple as hard as I would have to use the calculator, right? So yeah, so you would, in that case, if we're trying to keep the pressure the same, so I can lower the force if I lower the area as well. But assuming that we use the same amount of force is kind of is one way to another way to think about this that my high school chemistry teacher used explaining pressure. Has anybody ever gotten a back massage where somebody walks on your back? It feels really good, right? Would it feel as good if they were wearing stilettos? No, same force, right? I mean, no king shaming, whatever you're into, it's fine. But if you decrease the area for the same weight, you're going to get a much higher pressure, and that could cause very different sensations, right? So how do we describe this if we don't actually calculate the force of individual gas molecules? We could. There's basically just a way to use statistics to do that. But it's not really that's not the most effective way to do it. So, Connor, was there a question?
Yeah, so for like the ping pong balls, the door would close slower because the ping pong balls have some of their energy directed back, right? But the darts, more of their energy would go into the door if they stuck into it.
It's not a perfect analogy, but basically, but yeah, you would be able to throw fewer darts because the dart is going to be able to transfer more of its energy all the way into the door, as opposed to some of the energy going into it bouncing back the other way.
Like that for...
Although actually, I think it winds up canceling out because of the way the vectors work. The door has to exert force on the ping pong ball to get it to go backwards. So it shouldn't make a difference. It's basically the biggest difference is friction. You can picture throwing a ping pong ball at a door. It's not actually going to make the door move because you need to give it enough force to get it over the force of friction. If you had a really, really well-oiled hinge, then in theory, you could just throw ping pong balls and it should add up to the same total amount of force to get the door to close, regardless of whether it's a ping pong ball, a golf ball, or a dart. The difference with the dart that I was really trying to make was to get into this idea that the area matters. Not if they weigh the same as the ping pong ball and you throw it just as hard. And if we ignore air resistance, it should have. There's a lot of assumed in there, right? Like I said, it's not a perfect analogy.
This question might not really be answered, but if you were to go over the threshold for energy, would the door do anything back or would it just like slam?
So what would the door jam would have to exert force on the door to get it to stop. Otherwise, if you don't have something acting on that door, once that door starts moving, it'll continue moving until something acts on it to stop it. And so either the door jam has to do that or the air molecules hitting the door from the other side are going to be slowing it down, right? And has anybody ever experienced that where if you close your door the same amount you normally would, but your window's open, your door slams, right? That's basically because you're allowing the pressure inside your door and outside your door to equalize. And that actually means that those air molecules get out of the way better. you have just as many air molecules coming in behind the door as the air molecules are being pushed out of the way. When your window's closed and you do that, you're actually generating a small vacuum inside your room because you're kind of sweeping air molecules out of your room by doing that, right? If you can visualize these as tiny little particles, when you close your door, you're pushing a bunch of those particles out the door. And that's why your door slows down. But if your window's open, you're just going to bring in more molecules from outside as you're pushing the other molecules out with your door. And the net result is that you don't have you don't generate a pressure difference between inside your door and outside your door, and your door closes better.
So is that more of a physics thing or is it more of a chemistry thing?
Yes. Turns out that chemistry is physics, just on a really small scale. So this is actually talking about, yeah. So talking about gases in particular, and how chemistry and physics coincide is there's actually an upper division chemistry course called physical chemistry that is physics of chemistry of gases, and that's actually how you design things like internal combustion engines. Internal combustion engines are just little bits of gas inside those cylinders expanding really fast and pushing a cylinder when they do that, pushing the top of the piston. When that happens, that generates force and movement. And so, but the actual math behind that, you need multivariable calc to be able to do a lot of the math involved there, because you have, again, differential equations where you have changing volumes and changing pressures. But yeah, it's that whole field is called physical chemistry because it's the physics of chemistry. And incidentally, there are kind of two. There's classical physical chemistry, which is gases and pressures and volumes and things like that. And then there's quantum physical chemistry, which is what my grad school research was in, which is basically applying quantum physics to chemistry systems, but it's also a field of physical chemistry. All right. So if we have a balloon filled with gas molecules, that balloon is being held open, stretched out by the individual gas molecules in there, constantly bouncing around and bouncing off of things. Go back to you throwing your golf balls at the bedroom door. If you wanted to throw fewer golf balls to get the same effect, what would you have to do? Put more energy into each of them, right? Well, it turns out that's another one of these gas variables is temperature, because temperature is one way of looking at kinetic energy of individual molecules. The average kinetic energy of molecules in a system is equal to 1/2 mass of the molecules, mass of the gases, times the velocity of the gases squared. And that, again, that's going to be average. You increase your average speed of those molecules, you still have the same number of collision or the same number of molecules, and you still have the same area, but each one of them is going to hit with more force. Right? So what are some variables that, if we expand this, go back to thinking about gases, pressure of a gas that's going to hold our balloon stretched or push your door closed is based on area that you have for the gas molecules to run into and the force of each individual collision. And the force of each individual collision is based on how fast they're going, which means it's based on temperature. So basically we have three variables at play here. We have the area that the molecules can run into. So you can think of that as the surface area of the container. We've got how fast the gas molecules are going. And how fast the gas molecules are going, we measure by looking at temperature. And then what's the other factor? if you can't throw one golf ball hard enough to close your door at once, what are you gonna have to do? How many golf balls you have is gonna affect things, right? It doesn't matter what the I can't say it doesn't matter. The temperature of a balloon is going to affect the pressure inside the balloon, but what else affects the pressure inside the balloon? How filled it is, right? How many gas molecules you added into it. Landon? Say that again. So, and that is one of the units we use. What does PSI stand for? Pounds per square inch, not pressure per square inch, it's pounds per square inch. Yeah, PSI is one of the more common ways in everyday life that we see pressure. Anytime we're inflating something, we rate it in terms of pounds per square inch. Does anybody know what the standard atmospheric pressure is at sea level? 14, I think 14.7. That means over every square inch of your body, there is 14.7 pounds of force at sea level. How come it doesn't feel like that? How come you don't get squished?
Yeah.
Because what? Gravity? Indirectly. Because we equalize it. Basically, your body pushes back with the same amount of force. And that's why the parts of your body that have air in them, like your ears and your digestive system, can be really affected if you go scuba diving. Your lungs, your digestive system, and your ears are the most affected, because if you don't give your body a chance to equalize that pressure, then you wind up with it causing issues where the gas expands or gets compressed more. Because now all of a sudden it's not pushing back against the ambient pressure as much as it needed to be. You go down underwater every 12 feet, I think it is. Who scuba dives in here? Anybody? Is it 12 feet? Every 12 feet is 1 atmosphere of pressure. Does anybody, does that sound familiar? It's been a long time since I did my scuba class. But it's something like that. If you go down 12 feet underwater, the weight of the water adds another 14.7 pounds per square inch, which is why you've got to go down slow and come up slow to give your body a chance to equalize. 33, really that much? Huh. Oh, 10 meters. Okay. Josiah?
What's those like? What is there?
You're basically pushing the air back in so that you add as much air into your ears, so that it's got enough gas molecules it can push back as much to be just the same size. It does. In fact, if you go out into space without a spacesuit on, you basically remove all 14.7 pounds per square inch all at once. And if your body's pushing outward with 14.7 pounds per square inch, and then you remove that, that'd be like if you and your sibling were both pushing on both sides of a door and door's not moving. What happens if you let go all of a sudden? Slams, right? Think about that happening from the inside of your body outward by removing everything that's pushing in. Basically, your body kind of just explodes outward. What's that? Keep your eyes and mouth closed temporarily. Like, you can survive hard vacuum for maybe as much as 30 seconds. If you keep your mouth closed, if you keep your eyes closed, it's not going to be pleasant. You're probably going to have life-changing side effects for the rest of your life, as far as like you're not going to fully ever heal from that. But you probably could survive about 30 seconds. Exactly. And so that's the difference between scuba diving and being in a submarine. Is in scuba diving, you're allowing your lungs to become adjusted to the higher pressure. There's limits to what the human body can get used to, but turns out we can handle pretty high pressures if you give your body a chance to adjust. However, in a submarine or in the before they had scuba systems, they had diving suits. Those old school diving suits were basically, they were providing the force to push back. And that's exactly what they were doing. Yeah. Or Stuart and then Alyssa.
Same thing happened to you. So you said that, whenever you go, up really fast, you explode outwards, right?
Mhm.
The same thing happened when you're in the submarine.
If you're in the submarine or, yeah. So you can be crushed if you don't give your body a chance to adjust. Even a normal depth that you could scuba dive to if you went slowly. If you went from sea level to that pressure all at once, you could still wind up being crushed because you're not giving your body a chance to adjust. Your body needs to equalize your ears and your lungs, or else you wind up causing lots of issues. Did you have a question? Okay,
It's like the same thing.
okay.
Would it be the same, like, going down at the really,
So what's the difference between going down and coming up? So when you're going down, you can cause issues because you wind up getting pushed on, getting crushed if you go too fast. But it turns out that's actually less dangerous than going up too fast, because the other thing you're doing when you're going down is you're giving your lungs a chance to adjust, which means you actually wind up with more of the gas dissolve, more of whatever gas you're breathing dissolved into your bloodstream. And if you come up too fast, if you remove that excess pressure, you wind up with all of that nitrogen and oxygen that's dissolved in your bloodstream doesn't stay dissolved all of a sudden. So you wind up with bubbles forming in your bloodstream, in your brain, in your lungs, or in your extremities, which is, it's been described as being one of the most painful things in existence, is having bubbles in your blood. And if one of those is in your brain, you die. It's effectively like a stroke. You wind up with it basically popping a blood vessel in your brain if you're going into outer space.
yeah, like, part of the job is-
Exactly. G-forces can cause similar issues because it's very similar. You're putting extra pressure on your body, but it's not gas pressure, so the specifics wind up being a little different. Lisa? Basically just the extent, if you went down far enough outside of water, we were able to dig a hole 1.5 miles into the ground. If you went down that far, then yeah, you would wind up with the pressure increasing and the same general effects as us coming down from elevation to going to sea level. But the extremes happen in water because water is so much denser than the gas, and so it pushes with more force over a shorter area. Max and then Joe.
Going back to like the submarine, like analogy, what like happened with like the ocean gate submarine?
Basically, just it wasn't built to withstand it was built cheaply, as I understand it, and it did okay for a while, and then I think it had to weld fail or something like that, and then once you have one spot where it fails, the whole thing, you lose the structural integrity. Set. So this is also ignoring phase change, but yes, eventually if you compress a gas enough, it turns into a liquid.
Does it bond?
It still will have the same interactions. We're going to talk about intermolecular forces and polar molecules after break. That'll be one of the big topics when we come back, because it turns out phase change and those sort of interactions is dependent on pressure. You can get things to change phase at different temperatures by changing the pressure. So I'm going to leave it at that for now, because there's one or two more things I want to get to before we end for today, but I'm loving, these are great questions. And I don't want to give you too much of a heads up for what you're doing tomorrow. So this is actually kind of perfect that we're talking about these general ideas. Because what you're going to do tomorrow in lab is you're going to take. Is there a little gray bin on the back? There it is. I see it. So we're going to take these syringes that we have and use them to sort of mimic a balloon. Okay. So these syringes, we're going to treat them, they're a piston effectively, right? Where you've got a cylinder where three sides of this, where the round part and the bottom of the cylinder don't move. And the plunger going up and down is like the cylinder or the piston on a car cylinder moving up and down, right? So this is a way we can change the volume. And so what you're going to do is you're going to take these and you're basically just going to stop them so that you have a closed system of gas, similar to a balloon. Except that a balloon, if you squeeze one part of the balloon, the whole thing changes shape, right? Basically, what we can do here is if this is sealed nice and tight, we have a closed system of gas, we can add pressure to the system by basically just pushing on the top. And as you would expect, just like if you let go, if you squeeze the balloon, then let go, it goes back to the same size it was, right? If I push down on this and then let go, the stopper is going to go back up. I'm just holding this in one hand. It's not that particularly well sealed. What you're going to do tomorrow is you're going to seal this system. And then you're going to put various objects on top of it. You're going to weigh those objects and you're going to measure what the volume of the gas is. What should happen if you change the pressure, if we add more pressure to the top, if we add force to the top, it's going to compress it, right? And what happens to the pressure inside then? The pressure goes up when the volume goes down. Yeah, he's done. Okay. Thank you. If the pressure, we're expecting that as the volume goes down, the pressure goes up. Right, so we can say when the pressure increases inside the system, the volume decreases. That's our hypothesis for tomorrow. It's not much of a hypothesis, but because we all have some experience with this, we can all see physically what's happening. By squeezing this down, the volume's going to go down and the pressure is going to go up. And vice versa. If we started it in the middle, if I change the volume by pulling this up, the pressure should drop. And we can actually look at this as a graph. If we say, okay, we're going to look at pressure versus volume. Let's say we started right here at 1 atmosphere of pressure. We're not actually at 1 atmosphere of pressure, but let's just use that as a convenient number. And let's say we started at 1 liter. Obviously, this isn't a whole liter. I'm just picking easy numbers. If we double the volume, remember, pressure is equal to force over area. We double the volume, what would we expect to happen to the pressure? If the volume doubles, pressure should go down by how much? Half. It would make sense anyway. So it would make sense for them to be inversely proportional to each other. If you cut the pressure in half, the volume doubles. If you double the pressure, the volume gets cut in half. This is what you're going to show tomorrow, is you're going to actually make a graph that looks like this. What happens if we take this to the extreme? If we take it down to close to 0 pressure, we keep expanding the volume and expanding the volume. Could we ever actually get to 0 pressure? Would it though? Or would it just get infinitely close to 0, right? What do we call that in a math class? An asymptote. an asymptote. If you keep cutting the pressure in half, or I guess think about it the other way. If you keep doubling the volume, the pressure is going to keep being cut in half, but you can never get to zero unless you get to an infinite volume. Which means even in deep space, there actually is some pressure in deep space. Because even if your volume is the entire volume of the universe, that's still on some level a finite volume, which means there's still some pressure.
Does that make sense?
So would it make sense for us to have an asymptote here too? What happens if we keep cutting the volume in half? If we cut the volume in half, pressure doubles. What if we cut it in half again? Just double again, right? So we'll never actually be able to get to zero volume. If we have a closed gas, if this is a closed system, it doesn't matter. If I seal this up really well, it doesn't matter how hard I squeeze. I can't get it to zero volume because the gas itself has some volume, right? And it would take an infinite amount of energy, an infinite amount of force to get the area to be zero. And so we wind up with something where we're expecting, based on this thought experiment, that our pressure is going to be equal to some constant times 1 over volume. We're expecting this to be a 1 over x graph. That's
So is it above the value of the
just yes.
like 1 over x?
Yeah, because there is no such thing as negative volume or negative pressure for a gas. So we basically are only looking at positives. Last thing, last 10 minutes, we need to talk about the units for pressure real quick. We already mentioned PSI. One of the tricks with this lab is that we have a barometric pressure that Tom's is going to give you. That's going to be our average air pressure for the day. That it'll be something around 600 and, well, the way we measure that is using what's called a mercury barometer. A barometer is just a device for measuring barometric pressure. Baro means pressure, and meter means measures, right? So a mercury barometer is basically just a tube. It's a giant long test tube that's got a whole bunch of mercury in it. And it's got a pool of mercury that the open end is submerged in. What happens if you fill up a water glass in the sink and then you tip the closed end up? Will it dump out? What if you keep the open end underwater? It stays in there, right? What's keeping it in there? The air pressure pushing down on the surface is forcing it in there, because if the water didn't go to the very top, there would be some amount of vacuum at the top, right?
Yeah.
So what a mercury barometer measures is basically how high above the surface you have to get before the weight of the mercury is equal to the force, the air pressure pushing down on the surface.
It's not a stupid question. It's not like why not.
Could be. We'll go with that. I like a good kaiju question. All right, so all of this to say, one of the earliest ways to measure the barometric pressure was actually in millimeters of mercury. Millimeters of mercury sounds weird. It sounds like it's a distance, right? It is a distance. It's the distance above the surface of the mercury that you can go before the mercury stops rising. You wind up with this vacuum up at the top. And then you wind up with mercury in the tube here. The height here is based on the barometric pressure. So you're going to get a number in millimeters of mercury is actually the barometric pressure unit. Josiah, and then Macy.
Awesome.
Macy? Why mercury? Because mercury is really dense. It's got a density of about 14 grams per cubic centimeter, and it's a liquid at room temperature. You could use water. You can make a water barometer, but it would have to be about, well, 13 times longer. It winds up being about 10 meters above the surface of the water before the water will stop rising, just because water is not as dense as mercury. Mercury at sea level, the standard barometric pressure is 760 millimeters of mercury. So you still need something that's almost a meter long, a closed tube that's almost a meter long, where the open end of the tube stays immersed in the mercury. And then you can measure what that height is when it stops rising. And when you do that at sea level, your standard pressure is 760 millimeters of mercury. Right, so all this to say that there's a bunch of different units of pressure, and we have a sort of a standard value for all of them. We basically just relate everything back to the standard barometric pressure at sea level. Moving on.
All right, everyone, we have our winners from the Scholarship Fair raffle drawings. If you hear your name called, please come up to the office. We have 15 baseball caps donated by the Boosters Club for Ivan DeMullen, Juniper Brand, and Taj Teeter. Then Sir Optimist International of Tahoe Sierra donated two $25 Starbucks gift cards. They are going to Kevin Placencia and Aaliyah Fuentes. 3 more names have been picked for the Ernie's gift card. We have Angie Albanese. Come get your gift card. For the DJ Maxx gift card, Mars Lopez. And finally, for the Visa $100 gift card donated by Eldorado Community Foundation, we have the
Listen up.
Serenity Rider. Congratulations, seniors. Great job today.
Nice try. All right, last thing. I know we're almost out of time. All of this talking about units is because there's several different ways you can measure units. You can measure pounds per square inch like we talked about. You can measure millimeters of mercury. We have a standard number for both of those that's equal to what's called 1 atmosphere of pressure. And the last unit you need to pay attention to for this lab tomorrow is pascals. PA, capital P, lowercase a. Pascals is like pounds per square inch, except it's newtons per square meter. A newton is the metric version of a pound. A newton is 1 kilogram times meter squared over second squared. It comes from that kinetic energy equation. That doesn't matter that much. What matters is that if we want to calculate the force that we added by pushing down on this, if we know how heavy the object was in kilograms, and we know what the acceleration due to gravity is, we can actually calculate newtons by just taking the mass of our object times the acceleration due to gravity, which is 9.81 meters per second squared. So kilograms of your object times 9.81 meters per second squared is your force that's going to go into this. And then your area is going to be based on the diameter of this plunger. You're just going to treat it like it's a circle to get your area number. You're just going to measure the diameter of it. And if you know the diameter of it, you can get the area of the circle in meters. We need it to be in meters squared, right? So if you pay attention to your units, the lab for tomorrow isn't too bad numerically. The calculations aren't too bad, but there's a lot of easy places to mess up if you're not in the right units. Lisa? Meters squared. So when you measure your diameter of the plunger, you need it to be in meters, not centimeters. Because then we find the area of it, we can put our area down here in meters squared. And then if we have our mass in kilograms, then our force is in newtons. That gives us our pressure unit of pascals. right? And so if we know that we have our pressure in pascals, that allows us to convert back and forth just using a one-step conversion. Because we can say all of these numbers are all equal to each other. 1 atmosphere equals 760 millimeters of mercury, which equals 14.7 PSI, which equals 101,000 pascals. So this is going to be the way we standardize our pressures, because we're going to measure pressure in 2 different ways, but still need to add those numbers together. So just all that to say, pay attention to the units tomorrow and make sure you're measuring and writing down the right units. I would probably also be helpful to bring your Chromebook to write down your data, because we're going to do all the data analysis in Excel or Sheets. I know it's a good review though, because the take-home final for this class has a Excel question on it. Part of it. Two of the 12 questions on the final will be take-home. One of them will be Excel. So it's good review. All right, you guys can pack up. So this is the units. If the definition of a pascal is 1 Newton, which is a force, over a square meter. So this equals that. And force can be in a lot of different units. It can be in pounds, and your area could be in square inches. So basically, this is a pascal is just like PSI with different units. All right.